All right. It's time that we learn something new today. It's time we upgrade our knowledge. I think we're well, my webcam position leaves something to be desired here. That's a little bit better. I'll probably end up moving to the couch in a little bit. All right, so what are we doing today? I want to learn something new. I open up YouTube with no real plan of action or anything like that. I come across this. HTTP 1.1 must die. And really looking forward to this. I did not get to go to defcon again, much as I would have liked to. I am not yet great enough of a hacker to offer any sort of novel research as a presentation yet. That would be very cool. I think exploring the cutting edges is the most interesting part of this whole journey. Really taking the time to dig underneath the hood and understand how certain technologies works. So, who's James Kettle? He's a director of research at Portswigger. He's been doing this shit for a hot minute. I'm most familiar with his work in HTTP request smuggling as well as web cache poisoning. Goal today: consume the presentation, derive as much information out of it as we can. And I'm going to be taking physical notes on pen and paper during this process, as well as pausing the presentation to comment on my thoughts as well as any sort of viewer thoughts as we walk through this together. I might do some other stuff later too, but like I think this would be the most interesting thing to do right now. Afterwards, I'll take a break for lunch and all that stuff, and probably end up because it's like a 40-minute presentation. I imagine I'll probably have somewhere around the lines of like 20 minutes worth of commentary across the whole thing. Actually, it's going to be a little bit less since we skipped the first 4 minutes because it's just like defcon intro. So James Kettle has a public X profile. These are his favorite papers that he's written. Um, Pretty sure I've read most of these, but it's also the kind of thing that you would want to go through again because it's a rather complicated attack vector in terms of if you're like a complete newbie and you don't know anything about like anything. There is a pretty long pathway between like zero slate knowledge and really understanding exactly what is going on here. But anyone who already has the background in how web requests generally speaking work can at least start to pick up some of this attack. What's up? How you doing, Hollow Boy? So let me see here. Where am I? What's next? Um, so this is just one of his papers. Here's another one. Um, you have an opportunity to really learn a lot about how the web works in general by digging into the meat of what's actually going on with a lot of these attacks. Learn about things like web caches, proxy servers, the HTTP request protocol in general, as well as language parsing, programming logic, how to perform science in a way. That's fucking funny, Hollow Boy. Um, why does installing Nix? Maybe I have it backwards. You say you're unemployed, so you're installing Nix, but the way I read that is that you're unemployed because you're installing Nix. Sometimes two things can be true, and it's all about reversing perspective. That's fucking funny. Um, what? So you're not the first person to talk about using NixOS, man. It's like I always have to ask myself reasonings behind why, especially when I do it. Why am I trying a new Linux distribution yet again? You know, why reinvent the wheel constantly when, you know, eventually people find something that works really well for them. And a lot of people will tell you their favorite distribution and then give you a lot of different reasons behind it. But I'd like to just kind of take this approach where everyone's got a different use case and everyone's got like different needs. And so one distribution may not be the best one for everybody. So you can't really like push your own agenda onto other people without having like strong reasoning for like why everybody should use product A versus product B, right? That said, I've been pretty happy with Debian. Very few hiccups that I've run into, if any at all. The only exception is that maybe some of the software is just a little bit outdated, but for the thing that I ran into that for, I really didn't even need to do that. I was doing some shit involving like Scala and attempting to get like raylib bindings working with it, and I had to do some real workaround shit to like actually get it to work. And even then, like the end result was just like super undesirable. It was so slow. I don't know if I like this new ring thing. I've been trying to think of a new like ring, like phone notification sound that I could actually use as like a daily, notification sound, because I decided I was like getting tired of the Final Fantasy VII Fire sound effect, which I've been using for years now. But I don't know what I tried out the Final Fantasy IX Select sound, and I thought it was okay at first, but now I'm like getting kind of annoyed by it. No, no worries, no worries. Your English is fine. Well, okay, so you say for the infra thing, but like, why Nix versus like something like Arch OS, or like not Arch OS? It's just called Arch. Why not just Arch, or why not like Ubuntu, or you know what I mean? Like what does Nix offer over other distributions? Like most recent one that I tried that was new was Void Linux, and it was all right, but I actually ran into a real problem that prevented me from like wanting to really continue trying, the setup that I was rolling with. Basically, long story short, Void gives you the ability to mainline your kernel with either Muscle Linux, or sorry, Muscle C versus like libc, or glibc rather. Um, so I was trying it out on a friend's recommendation, and I had a new machine, and I was like, okay, it's probably a good idea to, now that I have like a fresh box, to try something new. And I was pretty convinced that I could like get all of my old configurations from my previous Linux, installs to actually work with the new setup, and it did, and it worked really well. I was able to get like just about everything that I needed built, but with one exception. That was a sprite, which is a great pixel art editor. It's almost non-negotiable that I have it in my setup now, and actually is non-negotiable because otherwise I'd be on Void still. So basically, long story short, there, um, you can manually build a sprite, and they give you like a GitHub repo and instructions, and I followed them, and I got pretty far into the process. However, the build could not proceed because the muscle distribution that Void is using, unfortunately, does not have what does it have? It doesn't have support for pthread create, or at least it didn't at the time when I installed it. So pthread create is part of libpthreads, which is basically the threading library in POSIX distributions. So this is kind of like a game breaker, right? Because I can't build the software that I need to be able to do pixel art editing. So instead of spend time trying to find like an alternative, I just said fuck it. And I felt like, lack of pthread creates kind of a big enough deal to justify like actually wiping the system and going on. In fact, I actually broke the system, so I kind of had no choice, because I attempted to upgrade my muscle library like live while the system was running, and it did not like that. I'll just say that much. let me pull up something here and then we'll continue. Shout out to everybody watching right now. I appreciate that. So let's dive into what this presentation is about, because time is ticking, and I feel like I've kind of given an intro to who this guy is. He's a very talented researcher. That's why he's director at Portswigger, which if you haven't used Burp Suite, you should, because it'll give you a clear idea of like just exactly what kinds of regular day-to-day tasks are involved in actually like attempting to like find out, you know, bugs in web applications, as well as websites, web servers, and other places. Learning the fundamentals of like how to actually make requests, how to read responses, how to parse these responses, how to read the various headers that might be sent to and from a server, and basically learning the interactions with a, you know, like a one machine to another in a way where you can learn how to fuzz and break and exploit vulnerable websites. So I'm imagining that this talk is going to be a combination of web smuggling techniques at a protocol level, as well as probably some stuff involving web cache deception. So it's probably like some combination of his previous material. So let's dive in.
What I was going to find. The plan was to neatly, so I thought I knew what I was going to find. The plan was to neatly wrap up a well understood attack class by finding some weird bugs and niche flaws in obscure systems, the long tail of desync attacks. But what I actually discovered changed both my perspective and the title of this presentation. So today, in this session, I'm going to share tools and techniques to enable you to embrace the never-ending horror of HTTP 1.1, navigate the desync endgame, and convince the rest of the world that it's time for HTTP 1 to die. This started back in 2019 when I realized that H1 has a fatal flaw. The isolation between individual HTTP requests is fundamentally broken.
So this is the premise for the whole thing, right? It starts with, you have to have a little bit of background as far as like what happens when you actually visit a website, right? So let's say it's like Facebook or some shit, right? You got like millions of users clicking shit every fucking day. So you got millions of requests coming in constantly, and everyone's got a different session where everybody's logged in and everyone's able to have persistent, you know, stuff, right? Like there's no sort of confusion, or at least not from the user end. And when you make a request, it hits a forward-facing server that's basically like the front. It's like when you call like a company, you have like a customer service representative or some sort of automated system picks up the phone and tries to direct your call to the right location, right? That's effectively what happens here, is that you have a request that you send to some website, but the website actually has like a representative or some server at the front of a chain that hits or receives your request first before it actually does something with it, such as passing it off to a second server. You know, this would be like a very simple case of this. So you effectively have like a proxy server that handles management of your requests at this point. So what happens when a bad guy is in there and he does something evil?
There's no single reliable way to tell where one request finishes and the next request starts. So an attacker who finds the tiniest parser discrepancy between the front end and back end server can cause a desync, enabling complete site takeover. And with HTTP 1 being an old, lenient, text-based protocol with thousands of different implementations, finding parser discrepancies was not hard. At the time, it felt like you could hack pretty much any website you wanted to. For example, I was able to show this could be exploited to get persistent control over PayPal's login page twice.
Holy fucking shit. Think about that for a moment. That means that anyone who attempted to log into like PayPal could have had their login information jacked and lost their control of their account. Just totally had a fucking, fucking account takeover. Goddamn.
But we knew what the solution was. If we deployed HTTP2 for the upstream connection between the front end and back end, then we could almost eliminate the entire attack class.
So to mitigate this, they were talking about making sure that you're always using HTTP to communicate from the proxy to the backend server. Suggesting that so long as you do that, then it doesn't really matter what front end serves up or handles or responds to.
So, 6 years later, what actually happened? Well, we didn't do that. We have started using H2 for the connection between the client and the front end, but then most servers just downgrade that request to H1 to talk to the back end, and that conversion actually makes the threat worse.
That's interesting. Also, should be unsurprising, but at the same time, I want to be surprised that it's not like set up as a default for these situations. Why is that?
And then, because we could see, well, okay, maybe that's not ideal. Yes, some things are getting hacked. We decided to bolt on the ultimate security measure, regular expressions.
Well, this is going to be fun. So, regex breaking is definitely a subclass of security in hacking. Like, you definitely want to get good at regex in general because of things like this. Generally speaking, it's not like in practice you're going to ever have to really do a super complicated regular expression. Knowing just enough to like work with the basics is usually probably more than enough. But at the same time, there are good demonstrations of like the kind of brutal things that you're able to do with regular expressions. Effectively, regular expressions is not a programming language because it's not Turing complete. However, it has been shown that you're able to do things like compute prime numbers with them.
The result is a mess. Here's a classic desync detection probe. You send to...
Before he explains it, let's try to break down what's here just to make sure that we're on the same page. So, what's actually happening here? So let's say you have two requests. One of them is properly encoded and the other is not. The first request, or this request, being the one that has some extra stuff attached to it, it's not going to work. However, if you attach the second request into the end of the first request, then we can effectively merge these two requests together in a way where we're going to bleed out some information.
Two requests, and if the target is vulnerable, the first one poisons the connection to the back end, so the second request gets prefixed with the text shown in orange.
Okay, so I had it a little bit off there. So it's actually this first request that's already the poisoned request. By attaching this extra request in there, this is what happens when a second request is sent after that. So this ends up being the full request that gets sent. What effect does that have?
Now, if you try this technique on a modern site, chances are the attack will fail even if they're actually vulnerable. That's because it'll get blocked by multiple regular expressions, or the gadget might not work on that target, or it might get missed due to the race condition involved in that technique as well. And there's an alternative timeout-based approach that avoids the race condition issue, but it gets blocked by even more regular expressions. So, to summarize, over the last 6 years, the industry has patched the detection methodology. They've patched the scanning tools, but they haven't fixed the actual vulnerability. This has created the desync endgame, where everything looks secure until you make the tiniest change to your approach. Let's take a look at an example.
This looks interesting. I'm not going to talk for a moment because there's like a really loud fucking lawn dude outside my shit, and it's a little bit hard to think.
A few months ago, I got an email from Vans saying he'd found a puzzling vulnerability and would like to know my thoughts about what was happening. The attack that he was trying to do was a pretty standard technique. You send a request that looks like this, gets downgraded to H1, poisons the connection to the back end, and the next person to access the affected site gets redirected to his server. And that redirection would get saved in a cache, enabling persistent cache poisoning of JavaScript files and giving persistent control over every page on the site. And the attack was working absolutely fine, except for one small thing, which is that the users that we were seeing being hijacked weren't actually trying to access the target website. They were trying to access random other websites, including things like banks, which is a bit weird. So clearly, the server setup doesn't look like this. And after seeing what infrastructure the target site was on, my first guess was that this was a desync between the Cloudflare front end and Heroku's reverse proxy, which would mean we were exploiting random websites hosted on the Heroku platform. And that was plausible, but actually completely wrong. It's not that simple. So I realized this when I tried to replicate his attack and went, hang on, this attack is getting blocked by Cloudflare's cache. So the attack isn't actually reaching the backend server, so there's no way that this could possibly work. But when I corrected his mistake, the attack stopped working. And I replied back in an email and said, it's not working for me. And he said, are you sure? And I went back and I tried his broken version of the attack, and it actually worked fine when you did it like that. So
the cache blocker is actually what was causing his attempts to fail, but not using the cache blocker apparently worked fine, which is interesting.
What that means is that Heroku has nothing to do with this. There was a period of time during which if you tested any website on Cloudflare and you did it correctly, you wouldn't find anything. But if you forgot to specify a cache buster, well then, you'd cause a desync inside Cloudflare's own infrastructure, enabling you to persistently compromise almost every website using Cloudflare. This is the desync endgame. Everything looks secure, but if you do one thing slightly wrong, you can end up hacking 24 million websites.
There you go. 24 million websites. You arrived Just in time, Dulce. Welcome. We're taking notes on Jason Kettle's recent DEFCON 33 talk, HTTP 1.1 must die. And so far in the first 6 minutes, he has shown us that he has previously been able to hack 24 million websites with one small technique. It's pretty damn cool.
How do bugs like that even happen? Well, partly it's the excessive complexity of the systems involved. For example, in this case, we know Cloudflare is receiving a request over H2, converting it to H1 for internal use, and then converting it back to H2 again to talk to the upstream, which is obviously not ideal.
That's a lot of levels of indirection. HTTP 2 to HTTP 1.1, and then back to HTTP 2. So internally, Cloudflare is using at the time was using HTTP 1.1. I'm sure they've upgraded since then.
But the underlying problem comes.
Wait a second. This CVE was issued in 2025. Holy shit. This is fresh.
From the foundation. There's this idea that HTTP1 is a simple protocol, and that makes it a secure foundation for whatever arbitrarily complex system you want to build. But the truth is that as soon as you start to proxy H1, it gets really quite complex. To illustrate that, here's 5 lies that I used to personally believe, and every one of these is going to be used for an exploit in this presentation.
Holy shit. All right, let's go through these. An HTTP1 request can't directly target an intermediary. An HTTP1 request can't directly target an intermediary. 2, an HTTP1 desync can only be caused by a parser discrepancy. 3, an HTTP1 response contains everything a proxy needs. To parse it. 4, an HTTP1 response can only contain one header blocks. And HTTP5, a complete HTTP1 response requires a complete request.
When combined, the last three lies here, taken together, mean that your proxy needs state just to read in the correct number of bytes off the TCP socket from the backend server, and you need special casing just to read in the headers before you even get to the body, and the entire response may arrive before you've even received the complete request from the client. This is HTTP 1. It's the foundation of the web, and it's composed of landmines that routinely expose millions of websites, and we've spent 6 years demonstrating that we're not able to fix it. It needs to die. So, how do we kill it? Well, we need to collectively show the world that HTTP 1.1 is insecure and that more desync attacks are always coming. And in the rest of this session, I'll show you how to do that.
Let's fucking go. That's what I'm talking about. Time that we step our hacking game up, really pick up some new tooling and some new infrastructure and some new knowledge base and understanding, and try to really take things to the next level.
First, I'm going to introduce a new toolkit to handle the desync endgame, and then I'll introduce two entire new classes of attack, exposing a few million more websites.
All right, let's take a look at this outline. Winning the desync endgame. 0CL desync attacks. Okay, so that sounds like a he's probably going to refer to one of these let's see. Yeah, so control, or I forget what the CL stands for. Content length. That's right. So, like, where was this? Here, let me pull this up real quick. So, one of the important tools used that, we're going to look at in time, seeing if there's a way that we're going to be able to reutilize or extend tools like Smuggler, which helps discover these some of these types of desynchronization attacks. So it's pretty cool and very easy to use. You can literally just like feed it a text file that has like different hosts that you want to try fuzzing on, and it'll get to work. And if there is a desync, it will let you know. So, and it'll even save the payloads used in the discovery of the desync itself, so that you can replay them in order to like use them in some sort of, attack vector.
Then I'll take a focused look at how we can escape this situation and wrap up and take some questions at the back. Now, during this session, I'm going to be roughly following the research journey. So towards the start, we're going to be gaining knowledge, but not very much by way of bug bounties. And then towards the end, as the knowledge that we've gained takes us further beyond the state of the art, things are going to rapidly get a lot more profitable. All bounties in this presentation were split equally between everyone involved. 100% of my cut of the bounties has been doubled by Portswigger and donated to a local charity, and all vulnerabilities in named targets have been resolved. So, how do you win in the endgame when there's regexes everywhere? Well, what you need is a reliable way to detect parser discrepancies. And back in 20, a reliable
All right, let's write this down. Rule. So winning the desync in game. Point 0. Don't use transfer encoding.
Way to detect parser discrepancies. And back in 2021, in a to detect parser discrepancies. And back in 2021, in a presentation at Black Hat Europe, Daniel Thatcher gave us one. And I was so hyped by this talk that I took the concept and I implemented an extra powerful version in HTTP Request Smuggler version 3.
All right, let's take a look at this. So, Daniel Thatcher did a presentation on practical HTTP request smuggling. So in his request smuggler version 3.0, permutation of every obfuscation technique, the various headers that you would try, multiple different strategies, and then whether or not there's an actual discrepancy found. So HTTP request smuggler three point oh. Okay, we'll check that one out too. Let's see. Oops, yeah. Okay, it's for use with Burp Suite. Naturally.
Which I've just released. This is an open source Burp Suite extension, fully compatible with the free version. What it does is it uses a broad range of techniques to analyze.
Compatible with the free version. Big ups. Fuck yeah.
And classify how the front end and back end are parsing the request and find discrepancies. For example, on this target, by looking at simply the status codes, we can see that if we use a space to mask a host header, then we get a unique result that's different to what we get if we just leave the host header out entirely. And just from that, we can infer that we found a parser discrepancy. This particular one, Oh,
that's very curious. So, in the fuzzing process, one of the things they do is they take a regular request, one that would normally work, and they're like, okay, feed that in. And they take that same request, and they mutate the capital H and the host header to capital X, attempt to send that, and then the backend might respond with 503. But then they add a space and the regular host word for that same header, and they get a 400. And then they attempt to do the X host again with the space, and they get a 503 again. So this is practical fuzzing in a nutshell. You basically take a target location and some sort of input that you're working with, and simply start manipulating the strings of that target. Try to change them in some way. that might change the response that gets returned when you actually send it to the server.
We'll call a visible hidden discrepancy because the masked header is visible to the front end but hidden from the back end. That scenario can usually be exploited to cause a CL0 desync simply by hiding the content length header as shown here.
So in this first attempt, or actually no, what they end up saying is this normal request would return a 404 not found, but when you feed this poisoned request first and the second request gets aggregated onto that first request, are all servers expected to give the same result? For example, if I wrote server code to make my laptop into a server, is this something I should test? And no, it's going to be on a server by server basis. You can 100% expect that implementations are going to widely vary. As an example, the way that Apache might handle something might be different from how Nginx might handle something. And largely too, the types of responses that a server gives are going to be something that's like configured or determined by either the application itself or the server that it's hosted on, or whatever like proxy or firewall sits in between you and that server. So as an example, Cloudflare might return a different response than if you directly connected to a server and then like actually sent the same request off. So totally something you could actually expect to be different for like literally every possible implementation of a server. And at the end of the day, even if like on a software level things are implemented the same way, there's still a level of configurability that says that like the site operator is really the one who determines that. So you would actually be the one who decides what server codes to respond with. So like as an example, a lot of different websites nowadays, if you attempt to like search up a page that like doesn't exist, it'll still redirect you to like a page that returns like status code 200, but like the page itself contains information suggesting that the page you were looking for was not found. Back in the day, and actually for many websites still, this error code is actually supposed to be 404, file not found. And what page gets returned based off of that is like configured on a server basis. What a lot of people used to do in the 90s is like come up with a really cool looking 404 page, like, hey man, looks like you were looking for that page but it wasn't found. We're gonna just, if you assume that you were brought here on accident, or something like that. I didn't realize requests could go through other software before getting back to me, such as Cloudflare. Yeah, essentially, it's like the web is a very big place, and the number of computers that your like request actually has to go through in order to get from your computer to like say Facebook or somewhere, it's a lot. You're talking like possibly 20 plus hops, depending upon where you are located, but in general, like a lot of the big corporate type websites have so many servers distributed around, but at the same time, you have to think, at the very least, when you make a request, your request has to go from your laptop to your router first, right? And then from your router to the next tier up in the networking infrastructure, which would be like, let's say you live on a domestic rural, neighborhood street where a lot of people have the same internet provider. So they're all probably going to have like a central node that controls like all of the different internet packets for everyone on that street. And then there's like yet another level up from there before it actually gets up to like the regional packet controlling infrastructures for your ISP, which at that point it gets shipped off to whatever's in between that and like the next level in the chain before it actually hits your servers and stuff. And you can actually trace this out using a tool called traceroute, which is a really fun activity if you're just starting out and you want to just kind of play around and like get a feeling of like how big the internet is, you know. You should try doing a traceroute like between yourself and Google, for instance. This is a really practical way to like take a look at like how many different computers does my request have to go through before it actually gets to Google. Can other computers change my request response if it goes through? 100%. Actually, this is how many companies have gotten in trouble for doing a technique, what they call a deep packet inspection, as well as content injection. In other words, there have been like not only ISPs, but also whole ass computer manufacturers who've been busted for like injecting ads into people's like response. Like, let's say you like asked for a certain web page. It's totally possible that someone in the middle is able to inject some sort of unasked for information into like the response that you receive. 100%. Actually, my ISP as well as X.com have both blocked my website, evildojo.com, in the past. And under certain circumstances, Spectrum still does block it sometimes. So yeah, totally.
But crucially, if you run into any issues when you're trying to convert it into a desync like that, well, you can adapt and overcome those problems because you know the underlying flaw. For example, on a different target, they were blocking GET requests when they had a body, but I was able to bypass that simply by switching the method to options.
Aha, the options method. He's saying that one of the techniques you'll need to apply is rotation of different request methods. So as an example, most of the requests on the internet are usually either GET or POST. In other words, if you ask for a website, you're going to basically get the website, right? And if you're like literally making a post to Facebook, then you're posting information. So very straightforward. But there are other request types, such as options, that basically return a response containing the list of different like allowed methods for that particular endpoint. And generally speaking, a lot of places don't really disable that method either. And as a site operator, you're totally able to create your own custom methods if you wanted to. It's just all about like the underlying server that you're running things on, and whether or not you're doing anything like super custom, you have to just like get into like learning how to configure this stuff. So it's totally possible you could actually spin up and create your own lab environment to like test a lot of these things, which is absolutely something that I am interested in doing. Because at the end of the day, what our end goal is going to be is, I'm sure the burp extension is great, but I like command line way more. So I'm going to want some command line tools for this kind of stuff. And if smuggler.py is not up to like the current state of the art or where this guy's at, then we're going to need to find a way to vibe code out some sort of upgraded solution for this, because I absolutely want to start testing this stuff again. It's absolutely, as he mentioned, not only such a huge problem, but also potentially very, very profitable. And we trying to get that money, fam. I want us all to get paid. You absolutely could. You could totally set up a website so that like when you curl it, you pass a custom method that's not any of the typical like HTTP methods, and then you return something very special for people who access the site that way. It would be very difficult and tricky to like get this to work in a browser, but you could absolutely do it in a way where you even build like a custom command line application that's designed to like interface with your custom server by using very secret methods and stuff like this. Totally possible. transient menu for security stuff. What language would you suggest for something like this? Learning Go? Actually, Go is probably a good target for like creating a custom server. I've seen the Primogen do this more than once on stream. There's a lot of really good network, like I almost feel like Go is created like for that purpose in a way, because like all of the people who are building like really fast like stuff, that Go makes it very easy to like spawn threads. That's one of the big reasons people like it. Another reason is also pretty secure in that like everything is statically linked, so there's no real problem there. But that doesn't mean that like you can't like write code that breaks or whatever. But that said, if you're actually looking to make a really fast server, I would stick with Go. I like Python a lot because it's very easy to like prototype ideas out and get them out there. And generally speaking, it's not like, like I'm going to be serving up so much, so many customers that like I couldn't use Python. You could totally use Python if you want to. I like Flask a lot. It's great for like just spinning up like a quick server to like test an idea out. I've actually used it for SSRF hunting in a number of different contexts. I managed to get something working with net package, found net HTTP confuses me. Yeah, honestly, like I'm not like the best with Go syntax. I've managed to sit down and kind of co-pilot out a few things that work, but I also just don't like the way that the Go packaging ecosystem works. I find it to be kind of like you really have to like put a lot of trust into things, and oftentimes like new things that you install with Go involve installing a fuck ton of other things that you didn't necessarily ask for, because the package that you're installing relies upon all of those things. So there's this like just level of trust and like vetting. Yeah, like I would so much like there's a part of me that wishes things were built differently with Go, but I mean it is what it is, and people like it, and there's a lot of people and companies doing millions and millions of dollars of business using it already. So it's not like a bad thing. I mean, I've done more Go than I've done Rust, even though like I recently had a realization about why I really should be looking at Rust a lot harder. But it's all about like what your real need is and how quickly you want to build things. And if I were just like trying new ideas out, I'm probably going to be doing it in Python. But if I'm actually setting out to like learn a new language, it's probably going to end up being Rust. C++ is not scary. No. I'm sick of people saying that shit. About to go off now. Holy shit. What's so scary about C and C++, really? Like, when I was in college and I had to take C, and a lot of people said this is the class that really makes or breaks people. It's like, why? Because of pointers. Say, okay, what's pointer? Well, pointer is basically just memory address. What really freaks people out about pointers, I think, more is the syntax of how you work with them. Because it's not intuitive. It doesn't, like, it's not clear to the layman when you're looking at code involving pointers what the fuck is even going on. So I get it on that level. But really, it's not so bad. People probably, I feel like, in my opinion, kind of blow things out of proportion. That said, though, memory corruption errors are still one of the largest threats to security today, which is one of the reasons Rust and stuff are kind of like becoming a thing. That said, It's not like Rust magically solves the problem, but writing your code in a very specific way does. And you can do that with any language. So it's not like you have to use language A or language B. In my opinion, it's largely about like use case, preference, and ultimately what your end goal is. I think C++ for me is a bit like Java. I tried both when I first tried to learn on my own. I couldn't get functions to work in either. Then spent 3 years bashing my head against JavaScript. Was going to quit, then tried C. I love C. A simple baby that takes a lot of maintenance. Yeah, C is straightforward. That's why I like C. There's no ambiguity. There's no question. You just write shit and it works. And if you make an error or if you break it, it's really on you. And I like that level of responsibility and control because it really forces you to take ownership over the whole thing that you're building, or as much of it as you can. The only reason that I've upgraded to C++ recently is because I realized I'm kind of fucking sick and tired of writing my own hash maps. Real talk. And the STL, the C++ standard template library, literally solves every major data structure headache that I was experiencing writing C. As much as I like C, as much as I love C, I still try to do things in a very C-like way, even in other programming languages. C++ is not scary. C is not scary. Rust is scary because of the syntax. That's the only reason. And even then, I feel like there's a way that Rust can be written that doesn't suck. Just like C++. Probably, but honestly, Dulce, probably not without using some sort of crazy macro wizardry. Yeah, well, do me a favor, guided, and if you don't want to see the ads, um, you can you can subscribe. So that would help me in the channel out. Really appreciate that. If you got one of those free primes every month, you could use that. Uh, you could also do some other things too. I'm not going to say what they are. Pardon my ebonics there. Yeah, Dulce, not without doing like a bunch of like black magic macro wizardry. And I did a little bit of that when writing my own little small unit testing infrastructure, which worked, and it was kind of cool to be able to like do that. But I also noticed that when working with macro wizardry on that level, it actually broke my LSP quite a bit. And I was no longer getting the kind of error reporting that I needed in especially in the unit tests themselves. So I have to be very careful about using that kind of stuff. It's naturally, there's probably a way to do it where I could upgrade the LSP somehow in order to accommodate for some of these things. But at the same time, I don't want to have to do a lot of reconfiguring if I can avoid it, because a lot of my process here is about just like getting rolling and getting stuff going and not having to like make or like the nice thing about my NeoVim setup is that I didn't really have to do a lot of configuring beyond just specifying which packages I want. That's it. A lot of the LSP stuff is kind of like automatically done for me. All I had to do was like tell it to use it to begin with. I appreciate that, guided. Thank you. I do apologize for the amount of ads. That's part of the the affiliate payout system that they got going, where you have to have a certain number of ads every hour in order to get like the maximum percent cut from the ads to begin with. It's not like I see shit for money on ads anyway, but I do I do appreciate you at least grinding through them. I am aware that it's the kind of thing that would put a lot of people off, and honestly I don't see enough people on that site to really honestly justify even having them to begin with. But in an effort to kind of like maximize or like figure out how to get best all of these different streams of revenue kind of rolling. Oh, my apologies. I should be more aware of when those are coming on. Let's get back to it.
It's that kind of versatility that makes this detection approach so valuable. It also achieves pretty good coverage by combining different headers, permutations, and strategies.
Okay, so this is kind of interesting. So given this initial request, tries a bunch of different rotations of permutations of the header host value, or the key rather, and ends up with some sort of request like this, where it fires back a 501 not implemented, suggesting that it attempted to process the request,
for example,
with ABC equals DEF as the HTTP method itself. Which is very interesting. So what happened here? He ended up having a bogus header followed by the content length with a space injected into the beginning of the content length key. Then it specifies content length of 7. So there are 7 characters here. A, B, C, E equals D, E, F. 7. So because of the space in the content length, it caused a desynchronization where it just began like reading the next method at the beginning of the body of this post method. Very interesting.
In this one here, we're still using the host header, and we're still using a leading space to hide the host header, but this time we're using a duplicate host header with a malformed value to reveal the issue. And in this example, that's revealed a desync on a web VPN used by a bank. This system even lets you predict vulnerabilities.
Oh, let's fucking go. Prediction. A recipient may recognize a single line feed as a line terminator. Early body pair. A, B, new line detection header. Expected outcome equals permutation outcome dot hidden. Whoa, whoa, whoa. Careful there, buddy. Thanks. Take it easy, man. Have a good one. So he's got this post request here where you've got a line, you got a new line, got content length, you got new line, you've got another header, AB, and then you've got an extra new line after that new line. But actually it's only so /r/n is like Windows style carriage return new line, but it's also like the web standard for like where everywhere uses. So expect 100 continue. Interesting.
For example, the RFC says you're allowed to accept a /n by itself as a line terminator, and the tool has detected on this target they're not doing that, which means if you place that server behind an RFC compliant proxy, there's a good chance it will be vulnerable. And we were able to trace that issue back to the underlying library, and a patch is on the way. The tool also flagged a whole load of servers running IIS behind Amazon's application load balancer.
Oh, fuck. Let's go back. Amazon load balancer to IIS. I'm pretty sure I've run into this.
A whole load of servers running IIS behind Amazon's application load balancer. As you can infer from the server banners here, this discrepancy is a hidden visible one. So it's the opposite way round. It's the front end that doesn't see the masked header. Now,
go to first request, throws back bad request server. Second request throws back no server header. Third request fires back the backend server, and then the fourth request returns back no server. But then AWS HTTP desync guardian tries to block desync attacks.
Now, these targets are protected by AWS desync guardian, and when I saw that, I thought, this thing's a bit of a pain to deal with. So I just put it on the shelf and thought I'd come back to it later. And while it sat on my shelf, Thomas Stacey independently discovered the same issue and bypassed desync guardian for a full exploit on those targets.
So to bypass Thomas Stacey, the single packet shovel.
The interesting thing is that even now that his bypass has been fixed, they haven't actually fixed the parser discrepancy. So these systems are still vulnerable to header injection, and to patch that, you have to change a couple of settings on your front end. Now, when I saw that, I went to AWS and said, hang on, why don't you just change these settings by default? Why not make it secure by default? And they said, well, some of their clients are using ancient HTTP clients which send malformed requests, and they couldn't possibly break those clients. So that's why things are vulnerable by default. Basically, when you use a cloud proxy, you're importing other people's technical debt into your own infrastructure.
This kind of explains why I've been able to like access other people's websites, given, because like if you attempt to if you like do a curl to like a Cloudflare IP address and then pass in a host header that's like, for instance, my website, because I'm hosted behind Cloudflare. Generally speaking, you can pretty much put in any arbitrary Cloudflare IP address with your target host and actually be able to get that content back. And I've actually been able to just like switch out the host header for other people's websites and get them as well, which is very interesting. Because normally it's like one IP address per website. Now you've got like potentially multiple IP addresses per website and lots of them.
This finding is where things started to go off on a little bit of a tangent, and I'm quite sad I can't name it because we're going to be talking about this one target for the next 10 minutes. It's another hidden visible scenario, and the obvious exploit of using transfer encoding doesn't work. So it forced me to ask, well, how do you cause a desync on this? What happens if you smuggle a content length header? That would be a 0CL desync, and these are widely regarded as impossible. That's because when the front end doesn't see the content length header, it only forwards the header block to the back end, and then the back end ends up timing out while waiting for the body to arrive. In other words, as soon as you try the attack, you get a server-side deadlock, which is great for taking down servers, but not very useful for desync attacks. Last year, while researching timing attacks, I stumbled on the solution. Whenever I tried to time how long it would take to load a static file served by Nginx, I would get a negative timestamp because Nginx was responding to my request before I'd actually finished sending it. This was a massive nuisance at the time, but it showed that sometimes servers respond to incomplete requests, which is something that would let us escape this deadlock. However, the target isn't running Nginx, it's running IIS. So how do we make IIS respond early to our request? Documentation is a wonderful thing, and this is an example of why. On Windows, if you use one of the following names for a file or a folder, the operating system will think you're referring to a device driver or something like that and then just blow up. So what happens if you hit that path on a server? Well, you hit a special code path which makes the server respond early without waiting for the body to arrive.
Ooh. Certain endpoints on IIS cause the server to respond early.
Thereby escaping the deadlock. That means that when the next request arrives, the backend will chop some data off the start of the request, and you'll probably get a 400 bad request response. Seeing this happen was quite an emotional moment for me for two key reasons. Firstly, I'd known about that /con feature for over 10 years, but this was the first time I'd actually been able to make use of it. And secondly, over the last 6 years, while researching desync attacks, I'd seen so many mysterious bad request responses that I actually made my tool report them as Mystery 400 findings, and this was the moment when I realized that all of those findings were probably actually exploitable. So, if you find a 0CL desync scenario, to make it work, the first thing you need is an early response.
Okay, this is critical. Zero CL desync attacks need an early response. Nginx, any static file. IIS, reserved file name. And other equals static file or server level redirect.
Gadget. Next up, we need to get beyond that the bad request response to something more promising. And you can do that by nesting a second request line inside the header block of the second request and adjusting the content length of the first request to slice out the data before it. This proves that there's a 0CL desync, but it's not a realistic attack because our victim is not going to conveniently contain a payload to exploit themselves inside their own request. What we need is a way to add our payload to their request instead of just chopping bits off. And we can do that with a double desync. This is where things get a tiny bit complex. So,
all right, they're chaining desyncs together. Fuck yeah. Double desync.
So this is a two-stage attack where the first request from the attacker causes a 0CL desync that weaponizes the second request that also comes from the attacker to cause a CL0 desync that means the third request from the victim gets exploited. This is the cleanest conceptual way to do it, where you simply chop the headers off the second request. But in practice, this rarely actually works because front ends tend to inject extra headers to requests before forwarding them to the back end, which makes all your length calculations incorrect. I'm releasing a script which works out the length of the injected header, but unfortunately, these headers often contain values like your IP address, which means even if you can identify the offset, your attack will work perfectly for you, but then break as soon as you give it to someone else. Fortunately, there's a better way. Most servers inject headers at the end of the header block. So that means that if your payload starts before that, your attack, although it now looks quite ugly, will be a lot more reliable. In this example here, I'm just chaining the desync with an input reflection on the website to reveal the value of the injected header, but by then chaining that with the head technique to merge two responses into one, I was able to serve malicious JavaScript to random live users of the website. There was a race condition involved in this, which caused me a huge amount of pain, but basically it just meant the attack would work reliably as long as you were sending a few hundred requests per second. Now, things got a bit involved.
A few hundred requests per second, fuck. So what do you do here? So the first request is a post to an IIS reserved keyword, and then they attach the following 4 requests, it looks like. So then they have a
there, but
they have the first like desync payload, which contains this second request. And then he actually is using a head request for this inner request. And then he passes in a cross-site scripting injection into the 4th request here, followed by like a normal request after that. Looks like someone needs a spanking.
But the good news is we've just published a Web Security Academy lab, so you can practice that technique yourself on a live system for free. And in about a week's time, I'll be attempting to do a live demo showing how to solve that lab. Now, with that technique, we were able to exploit a reasonable number of targets, with the best payout coming from XNS, and notably, most of those targets were vulnerable because they had a web application firewall. They would have been secure if they had not deployed that web application firewall in front of their website. Now at this point, I thought, great, we're done.
Shoutouts to my boy Sin from back in 2011. He was telling me that I needed to start learning how to hack firewalls even back then. And here we are 14 years later, and it's still like a massive problem.
Desync threat is finally fully mapped, and any future issues will be weird niche problems rather than big class breaks, and I can finally start to research something else. This is a mistake that I make every single year. It took the next discovery for me to finally realize the truth, which is that more desync attacks are always on the way. Back in 2022, I tried out exploiting the expect header, but I didn't find anything. But as it turns out, I wasn't looking close enough. The first clue that the expect header is something special is that it instantly broke Turbo Intruder, which is my HTTP client. And fixing it introduced a ton of complexity. And if something introduces complexity for a client or for a server, it's always way worse for a proxy. Expect is supposed to break sending a request into a 2-part process so the client can bail early in order to save bandwidth. No browsers support it, but because it's in the RFC and has been since forever, virtually all servers attempt to support it. But because it introduces statefulness into a core area of the logic that didn't previously need it, it raises a load of questions about edge cases. And basically, when you send this header, things go wrong. For example, on this site, the head request, which is a special case, works fine. And the expect header, which is a special case, works fine. But you combine the two and the server forgets about the first special case, tries to read too many bytes from the backend server and deadlocks. Now, that's the kind of flaw that you could predict, but you'll also find some more unexpected discoveries, such as the fact that on multiple different web servers, if you send the expect header, they just leak memory, including secret keys.
Whoa. Dude, what? What the actual fuck?
When I went to report that particular one, I found they'd just deleted their bug bounty program, which is not ideal.
Damn, get called the fuck out. Sounds like something that happened to me.
Now, because the expect header triggers 2 header blocks and all other responses have 1, it often breaks attempts by front-end servers to strip sensitive headers in order to hide them from end users, and thereby it reveals internal headers. And this technique works on everything on the Netlify CDN. And when I went to report that to them, they said, this is actually a feature, but they did pay me for it. But I don't think they fixed it, so if you need any of those values, it might come in useful. Now, around this time, I got a message from a small team of full-time bounty hunters who had also noticed the expect header making interesting things happen. And this kind of made me panic because, in general, a research collision is not good news. In fact, we lost a potential DEFCON presentation this year on SAML exploitation thanks to a different research collision. But this issue hadn't been published yet, and since I knew these people from their research on T0 request smuggling, and they already knew the technique, I figured we might as well team up. With my help, hopefully they'd make more money, and with their help, I should end up with more case studies. This was a good decision. We quickly found that by sending a normal valid expect header, you get a 0 CL desync on a whole lot of targets. So I'm going to focus on 2 in particular. On this one, was just a great interaction because T-Mobile gave us a $12,000 payout, even though it only affected a single pre-production server. And on this target, it only worked if you obfuscated the expect header value by adding a single character, and the vulnerable domain holds the attachments to the vulnerability reports sent to GitLab's bug bounty program, which obviously it would be quite nice to see some of those, wouldn't it? So on this target, we opted to go for response queue poisoning. This is a truly glorious attack where you smuggle 2 complete requests, which makes the server lose track of which response is meant to go to who, and just sends everyone random responses intended for other users. Now, it can be quite hard on low traffic servers like that target, but we persisted, and after sending 27,000 requests, we got access to someone else's private vulnerability report and a respectable $7,000 payout off GitLab. Using similar techniques elsewhere, we got some really quite nice bounties that I can't talk about, taking the total to over 100K. The expect header also causes CL0 desyncs. Basically, if you send expect, everything that might go wrong does. So this one affects every single website on our favorite, the Netlify CDN. And once again, we've got response queue poisoning, but this time it's affecting the entire CDN, so it's hijacking a continuous stream of responses from over 1 million different websites. Now, we found this vulnerability on a particular Netlify user that has their own bounty program, but because we were hijacking responses from so many websites, we couldn't actually get a response from that target, which was a bit annoying because it meant we couldn't report it to them. And then the issue mysteriously stopped working. So we said, okay, let's just report it to Netlify. And they said, websites using Netlify are not in scope and didn't pay us anything, which was a bit disappointing. And normally when I have a bad bounty experience, I don't talk about it because it just distracts everyone from the technical content. But this particular one is useful context as to something that happened shortly later. This is the last desync attack in this presentation, and it's a special one. It gave us full control over auth.lastpass.com, letting us serve content from entirely different websites on there and netting us their maximum bounty, but there was more to it. This technique worked on a large number of websites. There's a few select sites where...
All right, let's look at this one. So using the options method, request, some endpoint using HTTP1 on LastPass, and they're using the expect header again, but this time they're adding a space in front of the 100 continue, content link 39, and then they're wrapping in a request to sky.com, and then following it up with a legitimate another request to LastPass.
Of websites. There's a few select sites where if you find that you can hack them, you know that you're on to something really good. And with that technique, there was significant evidence that we could have used it to hack example.com. This would have been seriously cool because I bet they get a lot of interesting traffic. Unfortunately, they don't have a VDP or bounty program or anything like that, so it would have been illegal to prove it, and we will never know for sure. Hopefully I can persuade them to set one up and then have another go next year. Now, most of the targets were using the Akamai CDN, so we kind of had a choice here. Should we report the vulnerability to every affected company individually, or should we report it to Akamai only, and if they react the same way as Netlify did, not get paid? You can probably guess which option was more appealing.
Report to CDN and make less work and CDN happy, or less money, low visibility and risk of NDA, or report to companies, more money, kills HTTP1 better, more work, CDN does not like this, and risks technique leak. Which do y'all think is better? I'm not sure here.
It was a tricky decision for me because having a good relationship with a CDN over the long term is important. But when I collaborate with bounty hunters, I want them to make more money as a result of working with me, not less. So looking at the specifics of that finding, I said to the bounty hunters, well, you would have found this without me. So I'm going to sit this one out. You report it, don't put me on the report, and I won't take a cut of the payouts. This is a decision that I still have somewhat mixed feelings about, because they went on to earn over $200,000 from this issue. Overall, the reports were well received, but things didn't go entirely smoothly. It turned out that the vulnerability was actually fully inside Akamai's infrastructure, so they just got hammered with support tickets from their clients. I sit the bounty hunters is important for me because not get paid, report it the vulnerability CDNs. Now, kind of in way as Netlify did, not get paid. You can probably guess which option was more appealing. It was a tricky decision for me because having a good relationship with a CDN over the long term is important. But when I collaborate with bounty hunters, I want them to make more money as a result of working with me, not less. So looking at the specifics of that finding, I said to the bounty hunters, well, you would have found this without me. So I'm going to sit this one out. You report it, don't put me on the report, and I won't take a cut of the payouts. This is a decision that I still have somewhat mixed feelings about, because they went on to earn over $200,000 from this issue. Overall,
that's some good money.
reports were well received, but things didn't go entirely smoothly. It turned out that the vulnerability was actually fully inside Akamai's infrastructure, so they just got hammered with support tickets from their clients, and it seemed to be taking them a while to fix it. And because it had been reported to so many different companies, I got stressed about the technique potentially leaking before it was fixed. So I reached out to Akamai directly and got a $9,000 bounty in the process for that. But although they got a hot fix out for some clients quite fast, it still took over 65 days from that point to fully resolve the vulnerability. Overall, that one was quite a stressful experience, but at least I got some good US dollar backed evidence of the dangers posed by HTTP 1.1, as it took the total bounties earned to over 350K. So, all the attacks I've shown you are exploiting implementation flaws. So it might seem weird to say that the solution is to delete the protocol, but they all come from the same single protocol flaw, which is the lack of robust request isolation. It's compounded by two key factors. One is that HTTP1 is not simple if you're trying to proxy it, and number two is that we basically don't want to patch HTTP1 the right way because it would break support for legacy clients.
Okay, so the big takeaways here. Tiny bug equals complete site takeover. HTTP1 is only simple if you're not proxying. RFC landmines like transfer encoding, expect, connection, head, range. HTTP2 downgrading makes the situation even worse. We struggle to patch HTTP1. Normalization breaks too much. regex-based defenses aren't sufficient.
These factors all just combine to mean exactly one thing, which is that more desync attacks are always coming. To escape, we need to use H2 or 3. It's not the perfect protocol by any means. It's obnoxiously complex and it's binary, so you can't just read it. But it doesn't have the fatal flaw. So what that means is that the inevitable implementation bugs are going to be much lower impact. Of course, don't use HTTP2 downgrading. That just makes everything worse. So, to kill request smuggling, make sure your origin server supports H2 and then turn on upstream H2 on the front end, and the protocol will just take care of everything else. Note that you do not need to turn off HTTP1 for clients. That's because those connections are not shared between different users, which makes them significantly less dangerous. Unfortunately, some major players such as Nginx, Akamai, CloudFront, and Fastly don't support upstream H2 yet. So if you're stuck on one of those, there's some other approaches you can take to try to mitigate these issues. But I do not regard any of these as adequate long-term solutions. It's mostly about surviving until you can deploy H2.
So for people who are trying to set up secure servers, enable normalization validation on the front end. Regular scans with HTTP regulars or request smuggler 3. Avoid niche web servers. Apache and Nginx are lower risk. Painful but effective solutions are to remove all proxy layers or disable upstream connection reuse and don't trust internal headers.
The only way to use H1 safely is don't have a front-end server. We will be releasing more updates to Request Smuggler 3 as more techniques become known. So at least if you're doing regular scans with that, you'll find out relatively fast if you're exposed. Now, this is where I need your help. The number one problem that we've got is that people think upstream H1 is secure. So together, we need to show the world the truth. We need to show how broken it is by exploiting systems, breaking them, and sharing our findings with the message that more desync attacks are coming. And because we're in the desync endgame, and there's inevitably going to be future waves of regular expressions dedicated to breaking every detection method we can think of. Take my tools and techniques, but adapt them. Make.
All right, I gotta piss. Hold on. All right, let's finish this thing up.
Small changes and you'll discover a lot more vulnerabilities. For me, the key big research question is, what's the next expect? What other features in HTTP 1.1 have serious desync potential? The cool thing about this question is that H1 is so poorly understood that there's actually tons to find even beyond the realm of desync attacks. For example, it's well known that you can use the trace method to leak internal headers if the backend supports it. But what if the backend has disabled trace? Does that mean they're secure? Well, unfortunately not, because using the max forwards header, you can target an arbitrary intermediary server with that request instead.
Whoa. Okay, hold on. So, trace method. And hello, Nano.
So unless they've configured every server in the chain, the technique still works. Basically, HTTP 1 is an absolute goldmine for all kinds of research. There's a whole load of further reading available online, and you can find everything you need linked from http1mustdie.com. Note, this website is hosted on CloudFront, and that means it is actually using upstream HTTP 1, but if you can get a desync on it, we will pay you a bonus on your bug bounty.
Wait, what? Hold on. CloudFront.
Is actually using upstream HTTP 1, but if you can get a desync on it, we will pay you a bonus on your bug bounty. The three key things to take away are that this is not the end. More desync attacks are always coming. If we want a secure web, HTTP 1 needs to die, and together we can kill it. I'm going to take some questions at the back. I also have some t-shirts to hand out. Don't forget to follow me on social media, and if you have any more questions after that, feel free to chuck me an email. Thank you for listening.
Fuck, dude. That was great. I've got a whole ass page of notes here. lots of stuff that I have to kind of go over, lots of stuff to research. I kind of want to take a look real quick at request smuggler here. So he gives us a means to build it. He gives us turbo intruder that you also have to install. And then he's got labs on Portswigger for actually like playing around in practice. But I've actually managed to use, let's see, smuggler previously in order to find desynchronization issues. Now, I never got to the point of actually exploiting them because that's very hard and requires some pretty significant, like, request resources. You got to have a pretty fast server. You got to be able to like fire off lots of requests and receive their responses in a very rapid time fashion. So that usually requires spinning up like a VPS or something that's like pretty close to the target server and be able to execute something like that. Although that said, his tooling is really designed to be run locally. So, it's also possible to actually pull this off from that perspective too. Let's take a look, see what do we have in burp. So it's lots of Java stuff. Burp extender, burp scan wrapper. So a lot of this code is going to be using like burp's API. A lot of it's really just like automating the process of constructing these requests and then firing them off. And basically just like optimizing the request firing in a way where you minimize the amount of time between like actually sending each individual request off. Because in order to actually exploit these desync attacks, you do have to fire off like tens of thousands of requests at a time in order to sometimes get it to catch, because they don't always trigger and you don't always get back other people's content. I've never actually been able to successfully exploit the technique itself so much as actually find potentially vulnerable servers. It is a little bit tricky, but very clearly has a potential for not only doing serious damage, but also paying out really well. Implicit zero scan. Yeah, I don't see why like some of this functionality couldn't be like imported into Smuggler itself. I mean, obviously he wants us to use his tool, but at the same time, as an independent software researcher and developer, I find stuff like this a great example of a case where I would want to have a alternative available, because I don't necessarily always like using Burp Suite. So it's report due, so it actually Nothing really useful there, but each one of these individual scans is kind of like basically they just configure um, which headers to add and play with, and then ship off the request and then check the status. And this isn't anything that like we couldn't figure out how to kind of implement ourselves. Actually, building a desync tool in C or C++, I feel like might be a really cool side project. Like, I kind of want to start working on some more of my own scanning infrastructure and tools. And it would also give me a chance to like build another piece of software using libcurl, which I'm a big fan of. I don't know that it would be able to handle all of this stuff, but you know, we'd be able to take it to a point to see what it can and can't actually handle, and then from there we would have an excuse to like write our own version of curl or something like that, or fork curl and extend its capabilities somehow. I think it might be a good time for me to take a break, get some food, hang out with my animals, maybe do some solo coding and stuff for a bit, pick up my apartment, eat some food. I may have said that already. But we have learned a lot today in a short time frame. Had some good chats too. So, what you think, Nano? It's cool if we take a break, buddy. Yeah. Oh, careful. Don't fall off. Don't fall off, buddy. He's a good boy. So I'm a big fan of Smuggler because one, it's written in Python. Um, I don't think it's been updated in a long time though. 5 years ago, 4 years ago. So I think there's like a good opportunity to like actually extend it. So this basically defines like a request payload, header, body, method. It's a lot of stuff that you would pass into like HTTP requests. So I'm kind of curious, like how Smuggler fires stuff off. So they're using libpayload. Oh no, so they're using easy SSL. Um, Let's see, where does it actually fire stuff off? Okay, so here it's using easy SSL to actually do the connection and do the send. And then it gets the response kind of like socket style receive bytes. And then if it disconnects before timeout, we get an error. If the connection times out, it errors, but then otherwise it returns, success otherwise. So that's kind of interesting. So they're using easy SSL for actually handling requests. I wonder where is that initially pulled from? I think that must be his own custom thing added for that. I'm not finding anything on Google about it. So this is actually something that's handled by Smuggler. And actually, he's shouted out in the acknowledgments. So actually, like if I wanted to, and I kind of do, the question is going to be about like making sure that the upgrades actually work when I do them. Is to because like the way that Smuggler works, you can pass in a method to use for the actual request that you fire off, and you can do things like specify URL, specify vhost, specify timeout, and then the configuration files for the payloads. So like as an example, that you can specify them like this. So it's totally possible that we can not only upgrade the payloads list here to include some of those new payloads, but also upgrade the actual techniques that are used, so that we can add this automation of these, like this new class of desync attacks, 0.cl, in order to try and find some of these things, because I think it would be really cool to not only just pull it off, but also get paid for it. All you need is one to like get started. I need to get my baby up and take her out to pee pee. Um, Good chats, good hanging out with everyone today. If you're still here and you haven't done so yet, do me a favor and like the stream, follow me on my different channels, and until next time, as usual, take it easy, everybody.